Hi, I'm Gregory Green. I'm at Stanford right now. I'm a postdoc, and my work has mostly been on the structure of our Milky Way. So I'm going to talk to you today first about distances and how do we know the distance to anything, anywhere outside of the Earth. And then I'm going to talk about the structure of our galaxy. So before, though, I talk about all that, I just want to actually motivate. We'll give you like a taste of what actually I've created or what I've calculated. And this is a map of the dust within the Milky Way. So this is kind of flying through the Milky Way. And the Milky Way is basically a disk, so it's very flat. And what we're seeing here is starlight, but it's being processed and obscured by dust. And so you can see the dust in the plane of the Milky Way. Right over here, this is the region where we don't have any data, so that's why this is empty. But everything here we have data, and this is where the sun is. The galactic center would be in this direction. And these are all different dust clouds within our galaxy. And the distances to all these clouds are calculated based on data from about 1 billion stars. And I'll tell you within the talk how we figure out the distance to those stars, how we figure out where the dust is, and why this is important at all to astronomy. So the first thing in astronomy is that if you want to calculate a map of the Milky Way, you need to know how far away things are. And the first thing is, how do we know how far away anything is outside of the Earth? So if you think the nearest galaxy to us is Andromeda, and it's 2.5 million light years away. But how do we actually know that? You know, we've never actually traveled there. The farthest we've ever sent any probe is 146 astronomical units. That's 146 times the distance from the Earth to the sun. That's about 20 light hours, or about 1/billionth the distance to Andromeda. So given that we can only actually travel 1/billionth the distance to Andromeda, how do we actually know how far away Andromeda is? So a very long time ago, about 400 years ago, a guy named Johannes Kepler figured out basically what the structure of our solar system is. He figured out that all the planets orbit the sun on elliptical orbits. So if you plot out the motion of any of the planets, the sun will be one of the foci, there will be another focus, and the planet's moving on some ellipse. And the interesting thing about his model is it doesn't actually tell you how big the solar system is. It tells you the relative distance of everything. So it tells you this is how far Mercury is. And if we say the Earth to the sun is, we'll call that unit 1, then Venus is maybe 0.7 from the sun. And Mercury is maybe I think it's like 0.2 or 0.3 from the sun. So he figured out the relative size of the solar system, but you actually can't tell from his observations how big it is. The basic problem is you could scale this in any way that you want. You could scale it to make it larger or smaller, and all the angles to everything would be the same on the sky. So if we're sitting on the Earth and we look at, say, what's the angle between Venus and the sun? So we draw a line to Venus, draw a line to the sun. There's some angle between them. And that's all you can actually observe in the sky is angles. But those are insensitive to actually the distance. So it was a big problem for a long time to figure out, OK, what's the actual size of the solar system? And so the way that this was actually solved was by the transit of Venus. I don't know if anyone here remembers in 2012, I think it was, there was a transit of Venus. There was a lot of excitement, at least for us astronomers, it was very exciting. This happens only about twice in a pair every about 100 years. So probably no one sitting in this room will see another transit of Venus in their lifetime. And what happens is that Venus travels over the face of the sun within about a couple hours. And there was a Scottish mathematician named James Gregory who proposed that actually you could use the transit of Venus, observe it from different points on the Earth to actually figure out how big the solar system is. And the basic idea of this is what we call parallax. So imagine that we're sitting somewhere on Earth, and then Venus is here, and then this is the shadow of Venus and the sun. And imagine now you're lined up with the sun, and you've got Venus right in between it, and now you move up or down a little bit. You'll see Venus move up or down in the face of the sun. And how much it moves depends on how far you move and how far away Venus is and how far away the sun is. So actually, there was a very big effort to observe this shift. The shift actually, so this is sort of an idea of what it would look like if you're in the south of the Earth or the north of the Earth. And this is just sort of the Venus moves the opposite direction to the way that you move. But the problem is that this shift is actually very, very small. I've exaggerated it here by a huge amount. And the only way you can actually tell this tiny little shift is by measuring how long it takes Venus to move across the sun. So if you have, if you're in the north and Venus is traveling over a little bit longer of a distance, it'll take it a couple minutes more to travel over the sun. So there's this massive effort, actually, in which people traveled all over the world only to observe the transit of Venus. So Captain Cook's first voyage, actually, where he traveled all around the world, he went to Tahiti. His main mission was actually to observe the transit of Venus from Tahiti. And that was a critical measurement that allowed people to figure out for the first time how large the solar system is. So he went there and he drew these are pictures of his observations. And from Tahiti, they observed that the transit of Venus was a couple minutes longer than it was from Svalbard in Norway. And based on that, they actually got a 1% accurate measurement of the size of the solar system. So that's the first step. So now we know how large the solar system is, but how do we know how far away anything else is? So the way that you do that is that you look at the parallax shift of stars. So just as Venus appears to shift over the sun if you move up and down on the Earth, if we're orbiting the sun, and so we go around once a year, and our vantage point to the distant stars changes by a small amount. And so those stars appear to wobble just a little bit on the sky. And what happens then is you can actually relate the size of the solar system, so the size of the Earth's orbit, the astronomical unit, to the amount of wobble that you'll view in the stars. So the farther away, the smaller the wobble, so it's inversely proportional. And you can actually measure the distance to the closest stars. And so that was first done in the 1800s. And now we, of course, do it much, much better. And I'll tell you a lot more about how we're measuring it now. But the basic idea is, once you have this method of measuring distances to stars, you can relate the amount of wobble to you can measure the distance to the star versus the astronomical unit. Then we have the astronomical unit versus the distance between, say, Svalbard and Tahiti. And we've measured that in some way, which eventually goes back to some king's foot a long time ago. But you have this entire chain of measurement where this thing is calibrated off this, is calibrated off this, and eventually you get down to something that we can actually measure on Earth. So now we can actually say what's the closest stars to us, how to relate that to something actually that we can physically measure on Earth. So then I think people went to dozens of places on Earth to view it. And the problem is that sometimes you go there and then it's cloudy. And in one place it's cloudy, or the telescope didn't work. So there were only a couple of measurements that ended up going into actually determining the distance. But every 100 years, people then improved it. And now actually we can bounce radar off of planets. So now we actually have way better estimates of the distance just by looking for the echo. Yeah. So then you get this problem that this parallax shift is sometimes, it gets very, very small when we're talking about really, really minuscule wobbles of the star's positions. So when a star gets far enough away, you can't tell its parallax anymore. So what you have to do is you have to use other properties and use correlations between various properties to figure out how far away the stars are. So you measure a bunch of stars that are close by that you can see the parallax, and you establish some relations. This property relates to this property in this way. And so right here I'm showing you sort of the fundamental set of properties that we relate between stars. And this is the luminosity. So stars that are farther up here are brighter. And then this is temperature. So stars that are farther to the left here are hotter. And this is a whole selection of nearby stars that have measured parallaxes. So we know absolutely how bright they are, and we can measure their temperature. And you see they fall in certain regions of this diagram. And so if you then see a star that's too far away to measure its parallax, you can, for example, measure its temperature, and you can say, well, it should be this bright given its temperature. And then you see how bright does it appear to be, and you can use that comparison to figure out how far away the star actually is. So this is then the next step in the ladder of figuring out how far away things are. And so that's the step that you need actually to figure out, for example, how far Andromeda is, because it's too far to see parallaxes. So you can look at a couple different.
Can you repeat the questions? If you're going to ask a question, we've got mics.
Sure.
So go on to the recording. Otherwise, if you could repeat them.
Yeah. So the question was, how far away? How do you know the temperature? Sorry, of the star? And there are a couple different ways. I mean, you can look at the star's spectrum, and the spectrum tells you, where the spectrum peaks basically tells you how hot something is. The hotter something is, the higher the wavelength, or the higher the frequency of the light that it emits. So it emits higher energy light. So there are a number of ways that basically boil down to that, to figuring out the temperature.
What if the star is simply brighter? How do you account for differences in stars? I mean, just because something's brighter doesn't mean it's closer.
Yeah, so you have to actually use these relations. So you know what types of stars exist out there, because you've looked at all the nearby stars. So this is, for example, a catalog of several thousand nearby stars that have measured distances, because we can see the parallax shift. And you actually know that stars only live in certain parts of this diagram. They don't live right here, for example.
So it's just a statistical.
Yeah, it's a model. And then building on this, we then have also people who do computer simulations of how stars work. And so they have gotten very, very good at reproducing what we empirically see from first principles. You just put in some physics. So you have a ball of hydrogen, this amount of helium, this amount of other elements. Just physically simulate what will happen, and you actually can populate this diagram. They're getting very good at matching it. Yeah.
I would expect if you're looking in an older region of the universe that had older stars and older galaxies, that the statistical makeup of that particular area would be different. And do you then have to know that you're looking at
So
star formations?
Yeah, so this is getting kind of detailed, but yeah. So
take that into account also.
Yeah. So the question is, what about if you're looking at older stars that are, for example, older than what we have in the Milky Way?
Like in a region where there's a lot of older
Yeah.
stars.
So this is an issue, and so the biggest thing that happens is the chemical makeup of the universe has been changing, and so you have to, for example, look in the Milky Way to find the stars that have the chemical makeup that's most similar to the early universe. So this is detailed. We can talk about it afterwards, but there's a huge amount of work that goes into this. Yeah. I mean, there are people who build their entire careers off of that question, for example. Okay, so now I'm just going to give you a little bit of an idea of what kind of data do we actually use, or have I used in order to make this 3D dust map. And the major piece of data is called stellar photometry. So this is a typical sort of image that we might have in astronomy. We've imaged the same part of sky in several different filters. So we have a big telescope. We put a filter in front of it, and the filter only lets through a certain band of set of wavelengths. We take an image of the sky, then we change the filter, take another image, change the filter, take another image. Sort of like RGB, but we then have many more filters. And what we do is, we look at every single star. So we select, say, this star, and then we look at how bright it is through these different filters, and we get a series of measurements. And so this is, say, a red, yellow, green, and blue filter. And so this is like a very, very crude spectrum. But you can get a lot of measurements like this. So you turn every star into 4 numbers, 5 numbers, 10 numbers, however many filters you have. But if we take the same, well, actually, I'll actually ask you a question now. So there are these parts of the sky that look like this. And William Herschel in the 1700s called these things holes in the heavens. And there are these regions where you just don't see any stars. So do you have any ideas why don't we see any stars there? Dark matter? Dust? Black holes? Too far? Okay, the filters aren't capturing it. So I might have given this away with when I talked about dust earlier in the talk, but this is actually a dust cloud. And so what you have is, Herschel thought these are places that maybe the stars have been, he knew about gravity, and so he thought that maybe the stars have been sucked away because they've been pulled by some other gravitational things. But actually, if you look at these in the infrared, and you go farther into the infrared, you'll see that there are stars everywhere. And actually, if you look close to the cloud, you notice things start getting redder and redder as they get close to the cloud. Yeah?
I might have missed some information, but what do you mean dust?
I'll tell you in a bit. I'll tell you exactly. There are small particles that are just floating in space.
Okay, but like there's dust in this room, right?
Yeah.
It's flying all around this, and we can't even see it. It's
Yeah.
like, but you're talking about dust that can block out a star. That sounds big.
So we're talking about basically a very large cloud of dust. This thing is many light years across. And so if you were inside it and you had a flashlight shining, you would not tell that there's dust around you. But if that flashlight has to shine through several light years of dust, then eventually the light will get blocked out.
So when you say dust, in terms of speaking about dust in space, you mean the same kind of size as the dust in this room?
I am not an expert on dust on Earth, but
Like if you're right next to it, you can't see it?
yeah, it's the biggest dust grains are about 1 or 2 microns across.
Okay, so you
millionths of
mean
a
you
meter.
mean really small, even in terms of like the size of a person, not just in terms of the size of a star.
Oh yeah, yeah. I mean, this is millionths of a meter.
Okay.
So this is tiny little dust grains, but just a lot of them.
Okay. The reason I'm asking is because I figured that when everything is bigger in space, so when you said dust, I was imagining something bigger. Okay, so you
Yeah.
mean dust, like just dust.
Yeah, I mean really
Regular
just
dust.
dust.
Okay.
He's answered your question.
Yeah. Good question though. So these dust clouds, they really change how stars appear. So this is a star that I'm going to just assert is in front of the dust, and you can measure how bright it is through a couple different filters, so a couple different wavelengths. And now let's take another star, and let's assume that these are the same types of star, just for the sake of argument. And the measurements, and you can see it's much redder, and you can see all the filters are going down. So the brightness of the star is being decreased at every wavelength, but most at the short wavelengths. So blue is shorter wavelength than red. So at the short wavelengths, almost all the light's being taken away. And eventually, once you get down into this cloud, basically 100% of the light is being taken away in all the filters that we can see with the human eye. And if you go farther into the infrared, actually it becomes more and more transparent. So if you were to look at the same thing and say humans can see to like something like 800 nanometers. If you were to take an image maybe at 5,000 nanometers, you'd see stars everywhere here.
So this dust cloud is big enough that we can see a major blocking of light,
Yeah.
and therefore infer what stars should look like based on the properties that we can observe. But if we have smaller dust clouds that are harder to see or just at a smaller scale, how do we figure out if the stars are actually at the distance we're calculating or if there's other factors going on?
So there you need a statistical model where you have to have you have a parameter that you're trying to fit, which is how much dust is in front of the star, and you need to actually have a model that you infer, fitting to the data. I'll talk a little bit more about that in a bit though.
And then does this dust have any other gravitational, dark matter impact, or is it just there?
So the dust itself is not. So the dust is not dark matter. The dust is dark at optical frequencies, but I'll show you in a bit. If you look at other frequencies, the dust is actually very bright. But the dust does have gravity like anything, but it's a very small fraction of the mass of the Milky Way. The dust is, much less than 1% of the mass of the Milky Way.
Is this dust close to us so that we don't see many stars in front of the dust?
There's dust at all different distances, so I'll show you that later. There's dust throughout the Milky Way.
Well,
so
no, I understand that, but in this particular case, the fact that we don't see a bunch of stars in the foreground where the dust is behind it would imply that that dust is not really far away. If it was really far away, you're going to have
yeah, that's right.
stars.
So yeah,
Okay.
that's right. So I'll give you like a cartoon diagram of what a dust grain is. This is actually not an interstellar dust grain. This is a dust grain from inside our solar system. So it's, unfortunately, we don't actually have a single image of an actual dust grain from outside our solar system. There have been many attempts to catch them, but it's really hard because they come through the solar system at like 20 kilometers a second. And so if you try to catch them, they basically explode. So this is what's called a solar dust grain. But let's make believe that it's an interstellar dust grain. And this is, say, the Hubble Space Telescope, and this is a star that we're looking at. And that star emits light at different wavelengths. And some of the light just hits the dust grain itself and is blocked. Some of the light travels very close to the dust grain and then gets scattered away. So it sort of refracts around the dust grain. Or it's actually diffracts around the dust grain. And then some of the light reaches our telescope. And if you look at the ratio of what amount of, say, blue light versus yellow light or red light gets absorbed or scattered or passes by the dust grain and gets to us, actually more of the red light gets to us, and more of the blue light is scattered or absorbed. And so the star actually changes in its appearance, and the star ends up looking to us like it's redder than it actually is. So if you're trying to figure out what type of star this is and how far away it is, and you don't take into account dust, that's a big problem. The dust is also absorbing this light, so it's heating up.
Very simple question. Is this why a sunset looks red?
Yes, this is why a sunset looks red. That's actually a very good point. So we see this on Earth to a lesser extent. When the sun gets very close to the horizon, it looks redder because it's going through more atmosphere. So the dust is heating up, and the dust then starts emitting its own light in the far infrared. And we observe some of that light. So there are actually two ways you can detect dust. One is to look at how the colors of stars change, and the other way is to look at the emission from the dust itself. And so if you look at the sky in two different wavelengths, you see very different things. So this is in the visible. These are wavelengths that we can see. And you can see this is the Milky Way. This is the center of the Milky Way. And it's a disk that we're sitting inside. So you see fewer stars when you're looking out of the disk and more stars as you're looking through the disk. And you see all these dark patches. All those dark patches are dust clouds. If you then look at a different wavelength, so a longer wavelength, this is what the sky looks like. There you don't see any stars anymore, because this is at a much longer wavelength than stars are emitting at, but you see tons of dust. And so if you kind of look actually at some of these regions, for example, this region, which is called Ophiuchus, you can see it's dark in the optical, and it's bright in the infrared and millimeter. That's because this is dust that's emitting at dust is sitting at about 20 Kelvin, so 20 above zero. So the problem is, though, you can't use this data to figure out how far away the dust is. You can figure out how much dust there is, but the problem is the emission of the dust just all adds up, and it all stacks up. So it doesn't matter how far away the dust is. The brightness will be the same, basically, or the intensity that you observe. However, there is a hope with stars that you can measure the distance to the dust, because you can actually measure the distance to the stars, and you can tell how much dust is in front of every star. And so that's what we're going to do. But before I go on to that, I'm going to try to answer the question of why do you care about dust? So there are basically two types of people in astronomy. There are people who love dust and people who hate dust. And I guess I'm one of the people who loves dust, but there are a lot of people who hate it because it messes up all sorts of observations. You may have heard of the expanding universe, the fact that the expansion is accelerating, there's dark energy. That was discovered by looking at a lot of type 1a supernovae. This is a type of supernova that has the exact same, well, it has basically the same brightness. And so if you observe these supernovae at different distances, you can tell how far away these supernovae are. And there's a way to use that to determine the expansion rate of the universe. And I'm not going to really describe exactly what this diagram is, but I'll just say that this diagram is based on observing a lot of different supernovae. Each one of these is a supernova, observed really close and really far from us, and determining how bright each of them is. And different models of the expansion of the universe say how this diagram should change. And if you don't take into account dust, you will get this wrong. And you will say that there's dark energy when there is no dark energy, for example. If, just to give you an example, you'll get all the cosmological parameters that describe our universe wrong if you don't do this correctly.
Basic question. So, one second.
How do we define a supernova? Like you said supernova, so how do we define it, and how is it different than galaxy or something like that?
Oh, so a supernova is an exploding star. And this is an example of a 1A supernova in a nearby galaxy. And you can see that the supernova is almost as bright as the galaxy itself. And so for a very brief moment, one star in a galaxy, when it dies, basically, will become as bright as the entire galaxy. So in the Milky Way, this happens about once every 400 years. The last one was when Kepler was alive. There was a supernova. And so we're kind of due for another one, but it doesn't quite work that way. But anyways, so you can see these things at very large distances. So they're used to study the very distant universe. So that's why they're used to trace the expansion of the universe. But there's this one very special type of supernova that you can tell from its spectrum, called a type 1A supernova. And they really know that its brightness is very constant. So you can use this as they call it a standard candle. It's a way to measure how far away things are in the distant universe. There's been, over the last decade or so, a lot of work on finding exoplanets. So now we're finding all sorts of planets outside of our own solar system. And one of the primary ways that this is done is by looking for the small dip in light as a planet travels in front of its star. You see the brightness of the star decrease. So actually, if you want to know how big this exoplanet is, you look at how much of the light of its host star it takes away. And what you're actually doing is you're relating the radius of this planet to the radius of the star. But these stars are inside our Milky Way. They're behind dust. And if you don't know how much dust there is, you get the properties of the star wrong, including its radius. And then you get the properties of the planet wrong. So understanding planet properties, you need to know dust. The reason why you can't just measure the radius of the star is that actually this is an artist's impression. In reality, this is 1 pixel in an image. So you don't actually have the radius of the star. And then finally, if you want to know what our galaxy actually looks like, what its structure is, you need to actually understand where the dust is. So you can say how far away all the stars are and what their properties are and so on. This is a very nice artist's impression, but it is an artist's impression of our galaxy. A lot of things are uncertain here. Even the number of spiral arms is uncertain. So we know a lot more about how external galaxies look than our own galaxy. But there are a lot of reasons why it would be good to know the structure of our own galaxy, because we can study our galaxy actually in much more detail than we can study external galaxies. So, okay, hopefully I've convinced you that it is useful to study dust. Yep.
I have a question. I usually see very beautiful galaxy pictures, just like you put a camera over there, but I know it's fake, right? It's just kind of simulation.
So there are lots of galaxy pictures which are real galaxy pictures, like
this one.
Like this one is real.
How can you take this picture?
This is a Hubble picture. So actually, you can see galaxies from your backyard if you have a nice telescope. So it's worthwhile doing. I'll also just mention this is all dust in this galaxy. So you see the problem that we're dealing with. The reason why we can't get a nice image of our own galaxy is because we're sitting right, if this were the Milky Way, we're sitting right in this disk. And so if you look at anything, everything's just sort of piled on top of everything else, and there's dust in the way. So this is the big problem. But we'd like to know the structure of our own galaxy because we can study a lot of things about our galaxy in detail that we can't do in other galaxies. Like we can measure billions of stars in our galaxy and figure out exactly how they're moving and so on. So if we can connect that to some model of the structure of the galaxy, we could learn a lot more than we can learn about external galaxies. Okay, so hopefully I've convinced you that dust is important. And so the question is, how do we deal with it? And the answer is that we measure it, and we measure it very, very carefully, and we try to figure out in 3 dimensions where all of it is, and then we can correct for its effects. And so with this, I picked here a dust cloud which is far enough away that there are stars in front of it. And so you can see some blue stars that are kind of in front of this dust cloud. And I'm guessing that they're in front because they're blue and they're on the position of the cloud. If they were behind, they'd be red. But then you also see red stars that are probably behind the dust. Yep.
Are those actual colors? I mean, if you intensified the image, would you see those with the human eye in those colors?
So we didn't make any effort to calibrate this exactly to what the human eye would see. That actually would probably take a lot of effort. But these are wavelengths that you can observe, and we've mapped the bluest wavelengths to the bluest to B, and then the next bluest wavelength to G, and the next we try to map it in general in the right order. So it's close to what you would observe.
But it's not what you would call it, I think they call it false color image, where you intentionally use colors to highlight features that would be otherwise
No.
unobservable. So
No,
it
so
is
this-
pretty close to reality.
Yeah, so this is a project that I'm working on, and we didn't make any special effort to make these pictures look especially pretty or anything. This is close to what you would see, but we also didn't make an effort to make it exactly what the human eye would see, because that's difficult.
How do you know that the red star you see in the dust cloud is not in front of the cloud, but just red?
It could be. So that's something we have to take into account. There are faint red stars. So when you're doing this modeling, you need to take into account every single star. You need to figure out actually a probability distribution, density function. So a distribution of distances and reddenings that it could have. So this is something you actually have to deal with. And I'll actually describe this in a moment. So this is how we measure dust as a function of distance. So let's take some part of the sky, and let's draw a box around it, and let's make a very simple assumption that inside this box, the dust is only changing as a function of distance. So if a star is at some distance, it has this amount of dust in front of it, no matter whether it's here or here. So that's already an assumption that we're making.
You're assuming a universal distribution of dust.
In this one pixel. So it's only varying as a function of distance now. And we're going to use the different stars to trace how the dust is building up as a function of distance. So this is distance here. This is extinction of the light, which is a proxy for how much dust there is. And then we'll go through and we'll select each individual star. And we have a statistical model of what types of stars there are. And so if we observe the star to have this amount of flux in each of these filters that we're looking at, we can come up with a probability density function of here are the range of possible distances and amounts of dust in front of the star. So this is, for example, for one star. So to get to your question, for example, you could have it so that the star might have be close by and have no dust, or far away and have a lot of dust. So this could be a distribution that could be very broad for an individual star. So we do this for each star, and so we're figuring out for every star the range of possible distances and amounts of dust. And we do it for then all the stars in this pixel. And we see a bunch of different probability density functions, but there's actually only one distribution of how dust increases with distance. And it needs to be consistent with all these measurements. So we find sort of the curve of how dust is building up with distance that's consistent with all these stars. But actually, you can change this distribution, this curve a little bit and still be consistent with everything. And so what we do is we actually sample from a range of possible dust versus distance measurements. And so you can see in this toy model, there's a lot of dust around this distance, and then not a lot of dust. There's a dust cloud around this distance, but the dust is not really increasing at other distances. So we've sort of identified from this the distance of the dust. Now that's only in one pixel. And you do this on a couple million pixels over the entire sky. And so in every pixel, you're figuring out now how is dust increasing as a function of distance. So I'll show you the result of doing that. This is what the sky looks like this is what the galaxy looks like if you do that in every direction. So this is the southern hemisphere. We have no data yet. But everything that you can see from Hawaii, this is what every single line in here is one pixel where we've looked at a couple hundred stars and figured out where the dust is along that direction. So you do that for a couple million lines of sight, and then we have a model of where all the dust is, and we can now make different projections. So this is looking down on the Milky Way, where the sun is here. The galactic center would be actually somewhere over here. These might be spiral arms in the Milky Way. There's a lot of dispute over whether that's the case. But these sort of features that you see might be spiral arms. And then we live actually in something called the local bubble. where there's not a lot of dust around where the sun is. So that's one way of looking at it. This is with a couple of clouds overplotted. So each one of these lines is a cloud that people believe is in some spiral arm. So this is what people call the local spiral arm, the Sagittarius, Scutum, Perseus spiral arms. And you can see these measurements sort of line up with where we're saying the dust is. And then you can make these sort of nicer renderings. This is looking through the plane of the Milky Way, but away from the galactic center. So if you were to look on the sky, this would be sort of where Orion is on the sky. And this is called the Orion cloud for that reason. Then there are lots of other clouds. This is Taurus, Perseus. And I'm just taking a virtual camera and moving it around the galaxy, just orbiting around the sun. So you can see the parallax shift of the dust. In reality, you'd have to move faster than the speed of light and shift way too, make too wide of an orbit to actually see the parallax shift of dust. But just because we have a model, I can make any camera position I want.
Is there an estimate of the mass of the total dust in the Milky Way versus, stars? I mean, is it like a 1,000,000,000 to 1 ratio? Is it more like 20%? I mean, has anybody ever made that guess?
I think it's more like several hundred to 1 of stars to dust.
So the dust is not an appreciable portion of the mass of the Milky Way?
No, it's not,
Okay.
yeah. So the dust is mostly things like carbon and silicon, which are a very small percentage of the mass of the Milky Way.
Are
Yep.
there consistent locations where the dust is? Like
Yeah, so the dust
around stars,
the dust goes
around
into
solar
these
systems?
clouds, and these clouds are where stars are forming. So
Okay, 'cause
Orion,
you also mentioned that we don't really have a dust cloud around the solar system. So
Yeah.
is that just us or typically consistent?
so people don't know why we live in a bubble, but it may be because there was a supernova in the region where we are, several million years ago. But the dust is very, very clumpy. So, for example, Orion is the nearest region that has really massive star formation in the Milky Way. That's something like 1,200 light years away.
So then do stars give off a lot of dust when they form? Is that a conclusion we've been able to make?
Actually, stars give off dust when they're old, and then there are also processes we call it the interstellar medium, the stuff in between the stars. There are processes that lead to dust being destroyed and created. So there's a kind of balance in the interstellar medium of dust destruction and creation. So this is another video of basically we're just bobbing up and down the plane, the mid-plane of the Milky Way, and then looking back at the location where the sun is. The galactic center is over there. And so you can see all these different dust clouds that are in the vicinity of the sun. And then one more, this is sort of like a tour through the Milky Way. So we just went through Orion, and we're going to go up above the midplane of the Milky Way. So we're flying above the Milky Way, and we're going to start looking back towards the sun. You can see this looks a little bit like pencil beam structure. That's just because distance is hard to measure. So we know the angle to everything really, really well from the sun, but we don't know the distance to everything really well. So everything looks a little bit stretched out along the distance axis. So like, everywhere radially away from the sun. So the galactic center is over there. This is where we don't have any data. Now we're flying back towards the sun again. So we're passing through something called the Keeler Rift. This is the sun, and then that's Orion we're going to go through again. Okay. So that's based on trying to model in every single sight line, like I showed before, trying to model the amount of dust as a function of distance. And then you do that everywhere in the sky, and you have a model of where all the dust is in the Milky Way. So it's based on about 1 billion stars, about 3.5 million sight lines. Yes?
How long does it take to make one of those 3D dust models? I assume yeah.
I always say it takes like 40 days and 40 nights on a cluster. So it took us something like 1,000 CPUs running for
40 days
straight. Yeah,
straight.
40 days.
Wow,
Yeah.
that's crazy.
Oh, it's a good. How many images? I don't know off the top of my head, but these are. It's based on a project in Hawaii, which is taking an image every minute or so, every night for a couple of years.
This isn't
So.
the same as the, how do you pronounce it, Gaia catalog, or is this?
I'll tell you about Gaia in a moment. Yeah.
Okay.
So, one thing that we also come up with here is a stellar catalog. This is where the sun is, and this is sort of the density of stars that we observed in our Milky Way. The reason why there are lots more stars near the sun, and this is the galactic center. So in reality, there are more stars near the galactic center, but we observe the stars near our sun more easily. So we have a map now of the properties of stars throughout the Milky Way, or throughout a large portion of the Milky Way, which we're going to then use in the future to determine a lot more about the structure of the Milky Way. This is stars, this is a certain type of star, and taking only the stars that we have good distances to. And here you can see that there are more stars near the galactic center than near us, obviously. So this is something that we're going to be mining a lot in the future, but which we haven't had time yet. Yep.
So how do you anticipate how much this will change over time, or does this change very slowly on galactic scales, or does this kind of, how dynamic is this, all these distances and things with things moving and so on?
Over a human lifetime, none of this will change very much because the time it takes something to orbit in the Milky Way around where we are is about 200 million years. So, in 1,000 years, maybe we'll have to update the dust map a little bit. But yeah, it's basically fine right now.
Are you showing that there's no? Do you just not pick up the spiral arms, or?
You mean here? Yeah.
Yes.
So this is a very raw form of the data. In order to determine things like spiral arms, there'll have to be a lot more analysis of this. You need to take into account where you could observe stars. So, for example, where the dust is, in order to actually interpret what I'm showing you here right now. Yeah. Okay. So I'll try to show you something about the data that we use. This is a telescope called Pan-STARRS. It observed 3/4 of the sky, so everything you can observe from Haleakala in Hawaii. So it's sitting, high up above the clouds, every minute or so, every night, taking an image, and it's shuffling through 5 different filters. So it's getting us 5 numbers for every star. And this is the main source of data that I used to map the galaxy. They call the camera on it the gigapixel camera because it's a gigapixel. This is the proud creator of the camera, John Tonry, looking over his creation before they installed it. There's also a survey that was done both from the United States and Chile called the 2-micron all-sky survey. And it's all sky because the camera, the one in the north in the US observes the northern sky, the one in the south in Chile observes the southern sky. So you get a nice image in the near infrared. So this is just a little bit longer wavelengths than our eyes can see. So this is false color of the galaxy. Then there's Gaia. And Gaia is a project that's getting us parallax distances to 1 billion stars. And this data just came out, last year, basically. The data that was useful to me. And the basic way that Gaia works is it's sitting out at a place called L2, the Lagrange point 2, that's pretty far from the Earth. And what it's doing is it's rotating, and it has 2 telescopes that both project their images onto the focal plane, onto one camera. And they look for they're measuring the basically distances between all these stars. And if the stars are wobbling, the ones that are wobbling more, that are closer, will change more in position. And so the distances between the different stars will change on the camera. And they do this over many years, and they get lots of measurements, and they very precisely determine the parallax shift of all the stars. Parallax shift due to the Earth's orbit? Due to the Earth's orbit. And so this thing is just orbiting basically along with the Earth, a little bit farther from the sun than the Earth. And it's constantly sending back data, and that's being used to determine things all the way out to the galactic center. So all the way out to about 25,000 light years away.
How do they adjust for the movement of a star? I don't know if, I mean, could you in theory have a star that appeared here and then appeared here?
So the
that's
stars.
due to parallax, but then another case where it moved the exact same distance, but it was
So-
moving fast.
So you have to actually disentangle two things. One is the parallax wobble, and one is the constant motion, and they're different. The parallax makes things oscillate, and so you get both things. You get the distance to every star and how it's moving.
Yeah,
So it's
over
actually very
several
useful.
years, okay, yeah.
Yeah.
So is Gaia orbiting the sun or orbiting the Earth?
It's actually doing neither. It's at a place called L2. Well, it's mostly the sun, but it's at a place called L2, which is very special along the Earth-Sun axis. I can tell you more about it later,
Okay.
but yeah. So everything that we've done so far has been in the northern hemisphere, except for 2MASS, but we'd like to have, 2MASS doesn't observe in the optical, so we'd like to have visible wavelengths in the south. So I've been going down to Cerro Tololo Inter-American Observatory. This is a telescope called El Blanco at CTIO. And I've been observing the southern sky for a couple of years now. I'm just finished. And me and my collaborators, we've made a survey called the Dark Energy Camera Plane Survey, DCAPS. This really has nothing, we're not imaging dark energy, it's just the name of the camera. We're observing stars in light that you could see with your own eye if you had an eye which was 4 meters across. So we've observed about 2 billion stars over the entire southern part of the sky that we didn't observe before, or the galactic plane in the south. And all this data is publicly available. And if you go to this website, if you ask me, I can give you a link to it, and you can sort of pan around and view our galaxy images like this. It's sort of like Google Maps for the sky. I just wanted to mention that I won't really go into detail in this, but there was a problem that we had to solve in analyzing this data that we ended up solving with convolutional neural networks. The basic problem is that you look at a typical image like this, and you've got dust which is actually glowing in optical wavelengths. It's actually not dust, it's mostly hydrogen actually, which is glowing at optical wavelengths. And that's a problem, and you have to subtract that out. And it turns out it's difficult to come up with an algorithm which detects that, but you know it when you see it. This is what a normal image looks like. This is what it looks like when there's a lot of what we're calling nebulosity. And so it turns out that you can make an image classifier. It's a very simple thing to do, which tells you when this is a problem, and then you change your pipeline a little bit. So I'll skip the details of that. And I just want to say in the end, all this data requires, all the work that I've shown you requires data. In science, without data, we have nothing. That's what separates us from philosophers. And this comes from a number of very special places on Earth. One is Cerro Tololo in Chile. And this is a time lapse of looking at the Milky Way. This is a telescope that I use. And so this is a really special place. You're very high up, very dry. There's not a lot of clouds above you normally. And you get really optimal observing conditions here. Another place is Mauna Kea, which is it's actually the best place on Earth to do astronomy. And these are the Keck telescopes. And this place is really unparalleled on Earth. And you may have heard there's a controversy over it right now. But there's a plan to build really the next generation telescope here, which will really revolutionize a lot of areas of astronomy and tell us a lot more about the universe. And we also have to send things out to L2. So this is Gaia being sent out. And this is the Earth, the sun's over there, and this is L2. You can see it's along the Earth-Sun axis, and Gaia's doing this loop. I really feel this is kind of like James Cook's expedition, just in the modern day, to go to all these crazy places to to get data. So anyways, I'll just turn it over to questions now. It can be about, my work, or if you have any questions about astronomy, feel free to ask.
I have a quick question. According to your analysis, there is I know there is argue that whether the galaxy is collapsing or expanding. So according to your analysis, whether the galaxy is collapsing or expanding.
Well, our galaxy is stable, basically. So it's what they call rotationally supported. The galaxy is rotating, so it doesn't collapse or expand. Things are just sort of orbiting around the center. Yeah.
And don't confuse the universe expanding or collapsing with the galaxies. Those are two completely
Yeah, so the
separate-
universe is expanding, and it's expanding in an accelerating way, which is surprising to people in 1998.
Is there any thoughts? Sorry.
Yeah.
Is there? Go ahead.
In the beginning, I think you mentioned using radio to measure like nearby planets, the distance.
Yeah.
How do you do that through space?
Yeah, so there are very powerful radio arrays on Earth that are used to bounce radio waves off of Mercury, for example. These are only things inside our solar system. So they bounce radio waves off Mercury and look for the echo of them. You can tell how far away they are. And you can also measure various things about general relativity from that. Because relativity says that there should be a little time delay.
What's that echo though? Like how does that actually travel through space?
Well, you just have light. So radio waves are like light. They're just a form
I
of
see.
light.
Okay.
They can travel through space, and then they hit the surface of Mercury and bounce off.
Got it. Okay.
Yeah. Yes.
So they say that the stars are like sometimes they say that the stars are like millions of light years away, and we don't even know whether the star is right now there alive or not. We are just seeing the light now. Is it true?
Yeah, it's true. So the farther away you look, the light had to travel to you for a certain amount of time, so you're seeing it as it was back then. So everything in this room you're seeing as it was nanoseconds ago. The sun you're seeing as it was 8 minutes ago. When you look at Jupiter, you're seeing as it was several hours ago. When you look at the stars in our galaxy, you're seeing them typically as they were several thousand years ago. So, but then Andromeda you're seeing as it was 2.5 million years ago, so before there were humans.
Might not be there then.
Well, one star explodes every couple hundred years, so most of the stars are still there in our galaxy. Yeah.
Yeah, so my question is, when stars explode and form supernova, how long is it observable?
Yeah, that depends on the type of the supernova. So these type 1a, for example, they glow because it's nickel-56. There's a specific isotope of nickel, which has, I think it's a couple days, the half-life. And so the decay time of the light is actually based on something physically you can measure on Earth, which is, and actually the cool thing is, at very, very far away, it appears to be slower. I can explain that. It's a general relativistic effect. But they appear to decay more slowly when they're farther away. So.
But the answer is days. The supernova lasts days.
It depends on the type of supernova. There are different types of supernovae. So there are different ways that stars can explode based on their mass and what time. So the 1As are actually caused by something called a white dwarf, which is not, we don't,
Okay,
we
how
wouldn't
long
really-
do 1A how long do 1A supernovas last?
So a couple of days. It's based on nickel-56.
So those galaxy pictures which you were showing and the colored patches, those are the dust particles. Is that what it is?
Yeah, so the dark rings that you saw in that galaxy, where I was showing the supernova image.
No, the galaxy pictures when you were showing from the observatories.
Oh yeah, so that's the Milky Way pictures.
Yeah, the Milky Way pictures.
So
yeah, these dark patches, colorful.
yeah,
patches.
that's those dark patches are dust in our
Okay.
in our own galaxy.
Okay.
And would you see some? I mean, if you were up on one of these mountains, it pretty much looks like that. So
Yeah,
Yeah,
you
that's
can
what I
you can see that really clearly if it's a moonless night. So if it's a new moon or the moon hasn't risen, you can see that very clearly. Yeah. It's actually amazing. You not only see the Milky Way, you see the dust patches in the Milky Way. Yes.
Sorry if you answered this earlier on. 1 second. Late, but how do black holes affect the space dust that you're observing? Like, is there any effect due to their gravitational field? Are we seeing similar like pockets around them, or no?
So there's no special connection between black holes and dust. like everything else, dust is affected by gravity, so it will be attracted towards black holes just like everything else.
So would we expect to see concentrations of it around it or absences of it?
Well, some black holes have what's called an accretion disk of material that's falling into them. And then you can have dust in the accretion disk. But most of the dust that we see is in what's called star-forming regions.
Okay.
They're in these clouds that are basically in the process of collapsing and forming stars.
Got it. And then I think he was asking about it earlier, and I'm also curious about it. What is the L2 orbit that you were referring to?
Yeah, so L2 is what's depicted here, and it's a point, if you take a line from the sun to the Earth, and then you go a little bit farther away, it's a special point where there's a balance, the gravity of the sun and the Earth add up, so that if you're orbiting, you'll perfectly track the Earth. Normally, the farther away you are from the sun, the slower you orbit. So if the Earth weren't there, you would kind of trail behind the Earth over time, because you'd be orbiting more slowly. But it's just the added gravity of the Earth right at that point makes it so that you basically keep up with the Earth.
So you're like kind of falling in pace almost to keep
Yeah, you're
up with
falling
the-
exactly in pace, so that if you're sitting right at this point exactly, you'll basically sit in the Earth's shadow forever.
Forever.
It's unstable though, so if you move a little bit, you'll eventually fall out of it. So you need to do you don't need a lot of fuel to stay there though. You just need to push yourself back every once in a while.
Very cool.
I have a question about the Gaia there. Is there any consideration that, in terms of an exciting possibility for the future, that right now we have a billion stars map where they are? Soon, I don't know if it's going to take 10 years or 50 years, we'll have a position of all the stars and a vector of how they're moving. And that would open up possibilities for trying to interpret how maybe stars that have entered from galaxy mergers.
Yeah,
maybe
so this is
detecting black holes because the stars are tracking a little differently.
So stars are that's already being done. So Gaia does measure the motion of stars.
Do we have enough time?
Yeah, so Gaia only needs a couple of years to do that. So it's already done that. If you wait longer, so there's this idea of building another thing like Gaia in a different wavelength in 10 years, and that would give us much better velocities, because then you have a much longer baseline. The stars move much farther. But already Gaia is giving us, for hundreds of millions of stars, their velocity vector. The thing is, the second thing you said is the acceleration of the stars, so how the track changes. That's really tiny. So that is something that people are interested in, but it's at least a couple of generations of technological development beyond what we can do right now. People are talking about maybe mid-century, if there's like a Moore's law type thing for how well we can measure velocities. And if that keeps on going, then maybe mid-century we'll be able to do it. But there are a lot of hurdles to get there.
I have a question. Is there dust between galaxies, and also is that also affected by the expansion of universe? Is it moving out?
Yeah, there's very little dust between there's very little anything between galaxies. But yes, the galaxies are expanding away from each other.
We are already past time. People have to get back to work. Thank you so much for for coming. Other questions? Greg is here, and we're going for lunch, and you can join and discuss more. Also, if you want to show to your colleagues, your friends' work, your family's work, things that you think would be interesting to your colleagues, feel free to come and present those. The garage is yours. And seems that science talks are pretty popular, so we would do more of this, invite more scientists to come talk, maybe in a bigger room. Thanks.
Thank you.